At 8:40 this morning, Mountain Daylight Time, a blizzard warning was issued by the National Weather Service for a stretch of Interstate 80 inches Wyoming. Just 3 hours later, the same agency's office in Boston noted that temperatures for the following Tuesday would be 2 to 3 standard deviations above the established climate record, approaching the absolute maximum for this time of year. Here, we have a blizzard warning and a forecast for all-time May heat, both issued by the same organization on the same day. Across the country, 404 active alerts are in effect. 5 distinct and severe weather extremes are unfolding at the same time, and each one is being fueled by a single Rossby wave that has amplified into a pattern that climate models suggested should not be so common so early in the year. While some on social media have called this a convergence, the peer-reviewed literature has a more formal name for the phenomenon. We will explore what this atmospheric wave is, how it can generate both heavy snow and intense heat simultaneously, and examine the underlying factors that loaded the system. We will also look ahead to the next configuration and consider the unsettling reason why days like this are poised to become more frequent. For those who have been following the patterns tracked here on Calm Space, today serves as a stark verification. The next wave is already visible in the data, and we will be here to analyze it when it arrives. The day began as if the atmosphere itself could not decide on a season. At 8:40 a.m. Mountain Daylight Time on Monday, the 18th of May, 2026, the National Weather Service in Cheyenne, Wyoming, issued a formal blizzard warning. The alert specifically covered the North Snowy Range foothills along Interstate 80, including the areas of Arlington and Elk Mountain. The official text stated that blizzard conditions were already in progress, with wind gusts reaching 50 miles per hour and visibility plummeting to less than a quarter mile amid falling and blowing snow. The severity of this alert was classified as extreme, the highest possible tier of urgency the National Weather Service uses for winter storm events. The warning was set to remain in effect until 3 inches the afternoon. On this day, the state of Wyoming had 31 active alerts, the most of any state in the lower 48, excluding marine zones, a testament to the storm's localized intensity. Just 3 hours earlier, at 5:32 a.m. Mountain Daylight Time, the very same upper trough responsible for the Wyoming blizzard was being analyzed by forecasters at the Denver Boulder office. Their discussion noted that this trough was expected to travel across the state during the afternoon, bringing widespread precipitation with it. In the mountains, east-facing slopes north of Interstate 70 were forecast to receive a staggering 12 to 18 inches of snow. This led to a cascade of alerts. Winter storm warnings were raised for Rocky Mountain National Park, the Snowy Range, the North Laramie Range, and the Sierra Madre Range. The same warnings were extended to the Ferris, Seminole, and Shirley Mountains, placing the central Carbon County and the entire Wyoming high country into a state of simultaneous winter emergency. Meanwhile, as snow was already falling in Wyoming, a completely different weather story was unfolding on the East Coast. At 7:30 a.m. Eastern Daylight Time, the National Weather Service office in Boston was composing its morning forecast discussion for northern Massachusetts. The key message, placed prominently at the top, read, "Increasing confidence of record heat Tuesday for parts of southern New England." Further into the report, the office detailed the mechanics behind this forecast, explaining that an anomalous upper-level ridge would build over the area, bringing with it exceptionally warm, low-level temperatures. It is a technical, yet profoundly significant statement. The forecasters specified that temperatures at the 850 millibar level were projected to be 2 to 3 standard deviations above normal. This detail is crucial, as they noted it was close to the maximum relative to the CFSR climatology for this time of year, which suggests a period of truly anomalous heat. That single sentence is the pivot point for understanding the day's extremes. A National Weather Service forecaster, using standard operational language, is describing atmospheric temperatures at roughly 5,000 feet as bordering on the most extreme ever recorded for this specific time of year. The climate record they reference, the Climate Forecast System Reanalysis, or CFSR, is a robust dataset stretching back to 1979, encompassing 46 years of meteorological history. In their measured, technical prose, the Boston office was communicating that the conditions approaching on Tuesday were near the worst-case scenario within the entire modern record for that date. The result is a day of stunning atmospheric contrasts. On the very same morning, using the same set of weather products from the same federal agency, a blizzard warning is active in Wyoming, while an extreme heat anomaly is developing for southern New England. At the same time, the Storm Prediction Center has issued a moderate risk for severe thunderstorms across parts of Kansas, Nebraska, and Missouri, an extreme tier fire weather risk, the highest non-emergency designation used by the center, is in effect for the southern high plains. And to complete the picture, the Weather Prediction Center has posted a moderate risk for flash flooding in central Missouri. All 5 of these major operational extremes unfolded on the same calendar day, within the same 2-4-hour window, all driven by a single, continent-spanning Rossby wave. The full scope of the situation is captured in the National Alert Summary. On this morning, a total of 404 active alerts are in force from the National Weather Service. The specific mix of these alerts tells the true story of the day's atmospheric turmoil. The list includes 1 blizzard warning, 12 winter storm warnings, 19 winter weather advisories, 7 freeze warnings, and 6 freeze watches. Alongside these are 15 red flag warnings for fire danger, 1 fire weather watch, and a heat advisory, with more expected to follow. The list continues with 21 flood warnings, 10 flood watches, 3 severe thunderstorm warnings, 6 severe thunderstorm watches, 16 wind advisories, 19 gale warnings, and 27 air quality alerts. Every season of the year is represented in that catalogue of warnings. Winter products, severe weather products, fire weather products, flood products, and heat products are all active at once. The National Weather Service has seemingly exhausted the seasonal categories for its alerts because the entire annual cycle of weather is happening simultaneously. This is not a normal day. It was a day when the nation's weather map seemed to pulse with an unusual energy. A staggering 404 separate alerts were active. Yet what made the situation so remarkable was that they all stemmed from a single, unified piece of physics. One deep, upper-level trough was digging into the Great Basin, simultaneously ejecting energy out from the Rockies. In a synchronized movement, an anomalously strong high-pressure system, a Bermuda High, was anchored just offshore the eastern seaboard. These two systems were not independent. They were mechanically coupled, acting as two halves of the same immense atmospheric wave. The wave had amplified, and it was this amplification that was producing such widespread and simultaneous weather extremes. This extraordinary national weather story was captured with remarkable clarity at the Weather Prediction Center in College Park, Maryland. In the 8:30 a.m. Coordinated Universal Time discussion, a forecaster named Kong laid out the situation in 4 key messages that were distributed to local National Weather Service offices. The first message warned of another day of active severe weather and a flash flood threat across the east-central U.S., which would shift south by late Tuesday. The second highlighted extreme fire weather concerns across the southern high plains. The third described heavy, wet snow blanketing the higher elevations of Wyoming, the Front Range, and the Wasatch. Finally, the fourth message announced an early-season heat wave poised to challenge temperature records across the eastern U.S. In just 4 sentences written before sunrise, the entire weather narrative of a continent was told. A look at the state-by-state alert distribution reveals the sheer scope of the event. Wyoming was contending with 31 alerts, Missouri with 29, and Kansas with 22. The numbers continued down the list, with Texas at 16, California at 14, and Colorado at 13. Even states with fewer alerts, like Illinois, New Mexico, New Jersey, and New York, were part of this national tapestry of extreme conditions. There was simply no part of the country where nothing was happening. The eastern third saw heat advisories building, the middle third faced tornado watches and flood warnings, and the western third was under blizzard warnings and red flag warnings. Even the coasts were not spared. With rip current statements and small craft advisories, every operational meteorologist in the lower 48 was undoubtedly engaged. What is so uncomfortable, and yet so fascinating, about seeing all of this together is that none of the individual events were, in themselves, a surprise. A moderate risk of severe weather in Kansas in mid-May is not strange. A late-season snowstorm in the high mountains of Wyoming, while unusual, is not unheard of. An early-season heatwave on the East Coast occurs roughly once a decade, and fire weather concerns in the Texas Panhandle after a drought year are to be expected. The true story was not in any single piece of this puzzle. The story was the simultaneity, the fact that all these disparate events were unfolding at once, driven by one atmospheric configuration on the same calendar date. While the entire country felt the effects, the office that offered the most critical insight, written in the most careful and technical language, was Boston. This is because forecasters there were looking at numbers that approached the absolute maximum ever recorded for this date in their operational climate record. This is where the real headline was to be found. To understand its significance, we must look at the Boston number. Examining what 2 to 3 standard deviations means when measured against a 4-6-year baseline. We will translate abstract atmospheric data like 850 millibar temperatures of 18 to 20 degrees Celsius into the real numbers that would appear on thermometers. And we will explore what a major heat risk designation means for a region that has not seen such a threat in May for a very long time. The blizzards and tornadoes were dramatic, but the Boston number was the true measure of this event's extremity. The foundation for this type of scientific assessment is the Climate Forecast System Reanalysis, known as CFSR. This is one of the key operational climate datasets the National Weather Service relies on to establish a baseline for atmospheric anomalies. The CFSR record covers the period from the 1st of January 1979 to the present and is updated continuously. It contains a vast grid of data for temperature, wind, humidity, and many other variables at standard pressure levels, from the surface to the top of the atmosphere. It provides the historical context against which modern weather can be measured. For the heat wave that Boston was forecasting, one particular pressure level is of critical importance: 850 millibars. This level corresponds to an altitude of approximately 5,000 feet above sea level. The temperature at this height represents the temperature of the lower troposphere. This is a crucial detail because this is the layer of the atmosphere that mixes down to the surface during the day as the sun heats the ground, directly influencing the temperatures we experience. When the Boston office wrote that 850 millibar temperatures would be 2 to 3 standard deviations above the CFSR climatology for this date, they were making a very specific and potent statement. This involves taking the forecast model's output for Tuesday morning and comparing that projected temperature to the entire distribution of all 850 millibar temperatures recorded in the reanalysis for the very same calendar date over a 4-6-year period. A value 2 standard deviations above the mean falls within the top 2.3% of all historical observations. A 3 standard deviation event is even more extreme, placing it in the top 0.13%, or about 1 in 750 observations. In a 4-6 year record, a 3 sigma event might occur only once a decade, or even less frequently. 2 sigma events, while not common, are not vanishingly rare, but the detail that elevated this situation beyond a mere statistical curiosity was the specific language the Boston office used. They wrote that the forecast was close to the maximum relative to CFSR climatology for this time of year. Forecasters do not use such phrasing lightly. It was an operational signal that the atmosphere was approaching the highest value the reanalysis had ever recorded for that date in southern New England. They were signaling that we were entering the tail of the distribution, a territory that most people in the region had not personally experienced. But what does an 850 millibar temperature of 18 to 20 degrees Celsius actually mean for those on the ground? Let's translate this atmospheric data into human terms. The lower value, 18 degrees Celsius, is equivalent to 64.4 degrees Fahrenheit. This is the temperature of the air mass at 5,000 feet, which is poised to descend and shape the environment below. To understand the coming heat, we can look to the atmosphere thousands of feet above us. At an altitude of 5,000 feet over southern New England, the air mass arriving on Tuesday will have a temperature in the mid-60s Fahrenheit, or around 20 degrees Celsius. As this air descends and mixes down to the surface, it undergoes a process known as adiabatic compression, which naturally warms it. This warming occurs at a rate of approximately 10 degrees Celsius for every kilometer of descent, or about 5.5 degrees Fahrenheit per 1,000 feet. This simple atmospheric physics provides a clear and concerning picture of the coming heat. Over a 5,000-foot descent, this translates to roughly 27 degrees of warming. When you add that to a starting temperature of 64 to 68 degrees at altitude, you arrive at surface temperatures in the low 90s on the cooler end and approaching the low 100s on the warmer end. The official forecast from Boston, calling for mid-90s inland with potential for upper 90s in the Connecticut River Valley, is entirely consistent with this scientific model based on the 850 millibar level. Looking at the atmosphere from a different altitude reveals a consistent and powerful narrative. The forecast for the 925 millibar pressure level, which corresponds to about 2,500 feet above sea level, is even more diagnostic. At this height, temperatures are predicted to be between 24 and 26 degrees Celsius, or 75 to 79 degrees Fahrenheit. When this air mixes down to the surface, it requires very little additional warming to produce temperatures in the mid to upper 90 sets. Both pressure levels are telling the same story. The lower troposphere and the boundary layer are going to be exceptionally hot. The mixing process will be efficient because the air is relatively dry, with forecast dew points in the low to mid 60s. While this will feel uncomfortable, it is not catastrophic from a heat index perspective. This means the danger lies with the raw air temperature itself, which will be doing the damage. The official language from weather offices underscores the severity, moving from scientific data to public warnings. The Mount Holly office in New Jersey, which serves the urban corridor from Philadelphia to Atlantic City, framed Tuesday's conditions in similar terms. Their morning discussion spoke of an unusual and potentially record-setting early season heat expected to last through Wednesday. They projected high temperatures to be 10 to 20 degrees above normal, with many areas seeing low to mid 90s. A heat advisory was set to begin at noon for the urban areas of Pennsylvania and New Jersey, with an explicit note that temperatures and heat indices would likely be even hotter on Tuesday. They also explained that dew points would mix out in the afternoon, a technical reason why the heat index would remain close to the air temperature instead of soaring far above it. This detail again reinforces that the air temperature itself is the primary threat. Within the Mount Holly discussion was a sentence that reveals a critical and often overlooked, aspect of heat waves. The forecast noted that the air would be not terribly humid, but certainly uncomfortable since we aren't acclimated to it yet. This single observation points directly to the clinical reason why early season heat events are so operationally dangerous. It raises a crucial question about the difference between heat in May versus heat in August, and the answer lies in human physiology. The human body is remarkable, but it needs time to adjust. The process of heat acclimatization takes place over several weeks of repeated exposure. During this time, sweat rates increase, the composition of sweat changes to better conserve electrolytes, plasma volume expands, and the cardiovascular system adapts to handle increased blood flow to the skin. For the residents of southern New England, eastern Pennsylvania, and the New York metropolitan area, none of these vital adaptations have taken place. The region had been experiencing mild temperatures in the 60s and 70s until just this past weekend. This lack of preparation at a biological level is what transforms a hot day into a public health threat. As the Boston office explicitly stated, this is the first heat of the season, a type of event that is statistically more lethal per degree of temperature anomaly than the 7th or 8th heat wave of the summer. The acclimatization curve requires 10 to 14 days. The population has only had a weekend. The pattern of warnings becomes clearer as we move down the coast. The Baltimore and Washington office, covering the DC area, was even more direct in its Monday morning discussion. They warned of near-record warmth and described the forecast as one of the hottest days so far this season. They also cautioned that even hotter conditions could be expected on Tuesday, as an upper-level ridge of high pressure would reach its peak over the region. Their forecast for Tuesday called for highs well into the low to mid 90s, with a few upper 90s readings not being ruled out across the urban corridor and into central Virginia. This means Washington, D.C., was bracing for mid to upper 90s, Richmond for upper 90s, and cities like Hagerstown, Frederick, and Cumberland for the mid 90s. Further north, the New York City office, responsible for the vast metropolitan area, including Central Park, framed Tuesday and Wednesday with the term summer-like temperatures. Their forecast high for Central Park on Wednesday was 94 degrees Fahrenheit. This is a fascinating look inside the forecasting process, where meteorologists must interpret a model's known weaknesses. They specifically noted that weather models often have a difficult time getting hot enough in the vicinity of a front, a known low bias. In other words, the models have a tendency to underpredict the heat in these situations. The fact that the model blend still produced a 9.4 degree forecast for Central Park is telling. It strongly suggests the actual surface temperature is likely to land at the warm end of the forecast range, or perhaps even exceed it. Putting that 9.4 degree forecast into historical perspective is revealing. The all-time daily record high temperatures for May in Central Park are between 96 and 99 degrees, depending on the specific date. While 94 degrees is unlikely to break the daily record at that specific station, it still pushes the upper boundaries of the region's climatological history. The true significance of this heat wave, however, might be measured away from the most famous weather stations. It is almost certain that this event will produce all-time monthly records at several smaller stations across the region. These are the kinds of stations that have been recording temperatures for 150 years and have never, in their entire history, seen the upper 90s on a day in May. To synthesize these complex factors, we can turn to a modern tool for assessing heat danger, the heat risk scale. This is a product that the National Weather Service has been developing for several years. It is a 5-level scale, from minor to extreme, that moves beyond a simple temperature reading to provide a more holistic view of the threat to human well-being. It integrates temperature, time of year, the continuity of daylight, heat, and historical heat-related mortality and morbidity data into a single risk score for a given location. The major designation is the third tier, reserved for events with an elevated potential for illness and death, especially for sensitive populations and, most importantly, for people who are not yet acclimated. The data, the forecasts, and the public health tools all converge on a single, unambiguous warning. The official National Weather Service heat risk forecast for Tuesday across the mid-Atlantic and southern New England is major. This designation covers a vast and densely populated area, including Washington, Baltimore, Philadelphia, in the northeastern United States. A major heat risk is arriving far ahead of schedule. Such an alert in May is an operational anomaly. As the historical record shows, these events typically cluster in the hotter months from late June through August. While a heat wave of this magnitude does occur in the region every 5 to 10 years, depending on the specific location and its thresholds, its arrival tomorrow marks one of those exceptionally rare occasions. The intense heat may persist through Wednesday before a cold front finally moves in to break the pattern. For a region that has not yet seen this level of heat on its calendar this year, 2 consecutive days of a major heat risk present a significant public health challenge, prompting a story of widespread, coordinated preparation. Hospitals are bracing for an influx, cooling centers are being staffed, and emergency management agencies are positioning resources. For broadcast meteorologists, it signals the beginning of an intensely busy 48 hours. Yet, there is a deeper story behind the heat that many watching their local news will likely miss. The forecast for Boston is approaching the maximum possible temperatures relative to the CFSR climatology. The projected value for the 850 millibar level on Tuesday is between 2 and 3 standard deviations above the baseline from a 4-6-year reanalysis, placing this event firmly in the tail end of the historical distribution. This extreme temperature is not a random occurrence. It is the direct result of a powerful atmospheric wave. In fact, this is the very same wave that, on the same morning, triggered a blizzard warning over Interstate 80 inches, Wyoming. The heat blanketing southern New England is there because a Rossby wave on the continent's eastern side has amplified to such a degree that forecasters are using the strongest possible language in their operational vocabulary. And while one might assume the rest of this story unfolds along the East Coast with its cities and heat advisories, it actually lies on the other side of the country. The other half of this narrative is taking place in Wyoming. We turn our attention to the western side of this continental wave, specifically to the North Snowy Range foothills in south-central Wyoming. This area flanks Interstate 80 between the towns of Arlington and Elk Mountain. Here, the elevation of the interstate climbs from 6,500 feet to 8,000 feet, crossing a pass that has become infamous. Over the past 50 years, this stretch of highway has been the scene of more fatal winter storm crashes than nearly any other interstate segment in the nation. Locals know it as the Snowy Range Corridor, a section of road that the Wyoming Department of Transportation closes for an average of 50 to 70 days each year due to severe weather. Today is one of those days. At 8:40 inches the morning, Mountain Daylight Time, the National Weather Service office in Cheyenne issued a blizzard warning for that exact stretch of road. The official text is brief and to the point, describing blizzard conditions with additional snow accumulations of 2 to 6 inches and winds gusting as high as 50 miles per hour. Visibility was expected to drop below a quarter of a mile from the combination of falling and blowing snow. The warning was set to run until 3 in the afternoon. And within the operational metadata, the alert carried a severity tag of extreme. This single urgent warning was not an isolated event. It stood at the forefront of 5 separate winter storm warnings, all issued by the same office for the same day, painting a picture of a widespread and severe winter event. The scale of the storm becomes clear when looking at the series of alerts. The Sierra Madre Range was braced for 8 to 16 inches of total snow, with powerful 50-mile-per-hour wind gusts, creating periods of blowing and drifting snow, especially on the eastern side of the mountains. The snowy range itself, along with the higher elevation North Laramie Range to its south, was expecting 10 to 20 inches of snow, with the possibility of even higher local amounts, and winds gusting from 30 to 40 miles per hour. Further alerts covered the Ferris, Seminole, and Shirley Mountains, which anticipated 6 to 12 inches of snow and winds up to 45 miles per hour. Central Carbon County was forecast to receive 5 to 10 inches, with 4-5-mile-per-hour gusts. Finally, the South Laramie Range, including the Interstate 80 summit between Cheyenne and Laramie, was preparing for 7 to 14 inches of snow. When you tally the alerts, the picture is staggering. 1 blizzard warning, with 5 winter storm warnings stacked right behind it, all originating from a single National Weather Service office on the same day. And the storm's influence didn't stop at the Wyoming border. To the east, in Colorado, the National Weather Service Denver office elevated its own alert for the foothills above 8,000 feet to a winter storm warning. East-facing slopes, north of Interstate 70. Within the mountains of Rocky Mountain National Park and the Medicine Bow Range, were forecast to receive 12 to 18 inches of snow, while the lower foothills below 8,000 feet were expected to get 4 to 8 inches. This was not the only winter storm warning active in the country that day. In total, there were 12 such warnings in force, accompanied by 19 winter weather advisories, which represent a lower severity tier for smaller snow totals or more fleeting conditions. Across Wyoming, Colorado, and parts of Utah, 31 winter weather products were active in the middle of May, but it is the blizzard warning that stands out, flagged by the metadata as extreme. The criteria for such a warning are strict and specific. First, sustained winds or frequent gusts must reach 35 miles per hour or more. Second, falling or blowing snow must reduce visibility to less than a quarter of a mile. And third, these conditions must persist for at least 3 consecutive hours. The event in the North Snowy Range foothills met all 3 conditions, with winds gusting to 50 miles per hour and visibility dropping in the continuous snow. By official definition, this was a blizzard. To have a blizzard warning issued in mid-May in the lower 48 states is a statistically rare event. While not entirely unprecedented, a notable case in May 2017 closed major roads in eastern Wyoming and western Nebraska for 2 days. Such events are highly uncommon. The typical climatological window for blizzards in the high country of Wyoming runs from October through April. May blizzards are anomalies, the kind of weather events that long-term residents remember for years. They tend to occur when a deep upper-level trough, which should have dissipated weeks earlier, instead digs back down from the Pacific Northwest into the Great Basin and Central Rockies. This pattern pulls cold air down its backside, just as the eastern half of the continent begins to heat up for the summer. This specific atmospheric dynamic is precisely what was unfolding. The Denver-Boulder National Weather Service office articulated this mechanism clearly in their morning area forecast discussion. The 2 seemingly contradictory weather events, a dangerous heat wave in the east and a severe blizzard in the west, were not separate phenomena at all. They were 2 faces of the same powerful and deeply interconnected atmospheric system, playing out across the vast expanse of the continent. On Monday, a trough of low pressure migrating from the Great Basin moves over the area, bringing with it favorable mid-level ascent throughout the afternoon. At the surface, a crucial process known as upslope flow is occurring. This means that wind is being directed from east to west, pushing air into the rising terrain of the Front Range. As this air is forced to climb, it undergoes adiabatic cooling, its temperature dropping by approximately 10 degrees Celsius for every kilometer of lift. This cooling process eventually brings the air to its saturation point, forcing it to release its moisture. If the temperature at that altitude is below freezing, this precipitation falls as snow. In this specific atmospheric setup, the east-facing slopes of the Front Range and the Medicine Bow Range become zones of forced uplift, creating a perfect engine for generating heavy snowfall. When the trough is sufficiently deep and the upslope flow carries enough moisture, the result is the kind of significant accumulation seen today, with 12 to 18 inches falling on the eastern slopes north of Interstate 70. The same air mass responsible for this heavy snow is also creating blizzard conditions farther north. Along Interstate 80 and the northern snowy range, powerful westerly winds are channeled by the terrain as they blow down the backside of the higher mountains. The I-80 corridor, particularly through Arlington and Elk Mountain, is notorious for being the most reliable wind channel in the entire Rocky Mountain West. Here, gusts can reach 50 miles per hour, catching the falling snow and drastically reducing visibility. The consequences are immediate and severe. Roads close, and travelers who attempted the crossing this morning are now stranded in their vehicles, waiting for the warning to expire at 3 inches the afternoon. It is a stark illustration of how quickly conditions can change in this rugged landscape. The Sierra Madre range component of this system warrants special attention due to its sheer magnitude. An accumulation of 8 to 16 inches of snow, primarily on the eastern side of the range, is an extraordinary amount for the third week of May. The Sierra Madres are a lower elevation range situated west of the main snowy range. Their climatological records for May, averaged over the entire period of record, show they typically receive only 2 to 4 inches of snow during the whole month. Today, they are experiencing 8 to 16 inches in a single 1-2 hour event. The nearby North Laramie Range, which has higher peaks and a greater snow climatology, averages closer to 6 to 8 inches for the entire month of May. Today, it is receiving 10 to 20 inches. Similarly, the Medicine Bow Range, which the National Weather Service Denver office specifically highlighted in its warning, is being hit with 12 to 18 inches today, far exceeding its own monthly average. This kind of late-season snow event triggers secondary effects that, while not on the official alert pages, are immediately apparent to anyone living in the area. During the heaviest precipitation today, the snow line is dropping to about 7,500 feet. Below that elevation, the precipitation falls as cold rain, which saturates ground that is already wet from the spring thaw. This abruptly resets the timing for the spring runoff, which had been running ahead of schedule after a warm April. The presence of heavy, wet snow on top of an already melting snowpack can lead to sudden secondary runoff pulses as it melts. Consequently, crews are now carefully monitoring the Cache La Poudre and North Platte drainages, watching to see what unfolds over the next 48 hours. Across the state of Wyoming, the situation is no less dramatic. There are 31 active weather alerts today, the highest single state count in the lower 48, excluding marine zones. This complex mix includes a blizzard warning, 5 separate winter storm warnings, multiple winter weather advisories, and wind advisories for corridors not covered by the blizzard warning. As the cold air settles into the lower valleys tonight, freeze watches will also come into effect. Cheyenne is forecast to see temperatures drop into the upper 20 seconds to low 30 seconds Monday night, while Casper is expected to fall into the mid-20 secs. On the morning of May 18th, the state is effectively experiencing a full-scale winter event, with operational alerts issued by the National Weather Service because the conditions absolutely warrant them. However, to truly grasp the significance of this event, it is essential to understand a critical connection. The very trough digging into Wyoming and producing this blizzard is the same one ejecting atmospheric waves into the Central Plains, which are fueling a moderate-risk tornado outbreak in Kansas and Nebraska. This reveals a deeper reality. The trough is merely the western half of a single, vast Rossby wave that extends from the Pacific Northwest all the way across the continent to the western Atlantic. This interconnectedness raises an unsettling question about the nature of our weather systems. The eastern half of that same wave is a ridge of high pressure, which is anchoring the Bermuda High in place off the east coast. This is the feature responsible for making the 850 millibar temperature over Boston 2 to 3 standard deviations above its climatological average for Tuesday. The same wave is simultaneously producing both extreme cold and extreme heat. The Wyoming blizzard and the New England heat dome are two faces of a single atmospheric configuration. They are not coincidences or separate stories. They are the direct mechanical consequences of the same piece of atmospheric physics, playing out on opposite ends of a wave currently locked in a high amplitude, low phase speed resonance, a phenomenon that has been the subject of climate science papers for the last 5 years. This is where the inquiry becomes uncomfortable. If the same wave is responsible for both of these extremes at the same time, one must ask what the wave itself represents. What we are seeing is a piece of physics that is happening more often, with greater amplitude, and earlier in the year than models had predicted. The technical literature describing this configuration does not tell a comforting story. It tells a story of the atmosphere learning a new behavior. And this new behavior is precisely what we are watching unfold on the morning of the 18th of May, 2026. This is one wave with two faces. A Rossby wave is a planetary scale undulation in the mid-latitude westerly winds, named after the Swedish-American meteorologist Carl Gustaf Rossby, who first described their basic dynamics in a 1939 paper. The physical mechanism behind their formation is a combination of two fundamental principles. The first is the Coriolis effect, the apparent deflection that any object moving within a rotating frame of reference experiences. As the Earth rotates from west to east, any parcel of air moving across its surface is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. The second principle is the temperature gradient between the equator and the pole. The equator is warm and the pole is cold. Warm air over the equator tends to rise, while cold air over the pole wants to sink. To keep the global system in balance, air is constantly transported between these two regions. When you put these two forces together, a remarkable pattern emerges. High in the atmosphere, a vast river of air flows between zones of different temperatures. This movement, deflected by the planet's rotation through the Coriolis force, gives rise to the mid-latitude westerly wind. This band of air, found between roughly 30 and 60 degrees latitude in both hemispheres, encircles the globe in a constant west-to-east current. Yet, this river does not flow in a straight line. It meanders in giant, undulating curves. These immense planetary-scale ripples are known as Rossby waves. Their wavelengths can span from 3,000 to 6,000 kilometers, while their amplitudes may vary from a few hundred kilometers to more than 2,000. In their typical state, the entire wave pattern drifts eastward at a phase speed of about 15 degrees of longitude per day, meaning the global pattern advances a distance comparable to that between Boston and Detroit each day. This steady, predictable motion forms the very pulse of our planet's weather system. Under normal conditions, these Rossby waves perform their function almost invisibly, acting as the great regulators of our atmosphere. They are responsible for our day-to-day weather, diligently mixing warm and cold air across the continents. For the most part, they effectively contain the frigid polar air at higher latitudes, though they do permit occasional spills of cold air southward in winter or warm air northward in summer. Meteorologists can visualize this process by tracking the waves on 500 millibar charts, which show atmospheric conditions at a pressure level corresponding to about 18,000 feet. On these maps, the wave structure becomes clear, revealing its troughs and ridges as distinct dips and bulges in the global wind pattern. But what happens when this orderly progression breaks down? Under certain circumstances, which are now the focus of intensive climate research, these waves can behave very differently. They cease their modest, steady march and begin to amplify. The troughs or dips plunge much farther south, while the ridges or bulges extend far to the north. At the same time, their eastward movement, or phase speed, dramatically slows. Instead of progressing at 15 degrees per day, the pattern may slow to 5, 3, or even come to a near-complete standstill. The wave becomes locked in place, forcing the same regions to remain under the same ridges or troughs for days on end. It is in these moments of atmospheric stagnation that the most severe weather consequences unfold. In recent climate science, this dangerous phenomenon has been given a name: quasi-resonant amplification. The concept was formally introduced in a 2013 paper by Vladimir Petukov and his colleagues, published in the Proceedings of the National Academy of Sciences. Their research revealed that when Rossby waves of a specific wavelength become trapped in the mid-latitudes, their natural eastward movement can be halted by conditions in the polar jet stream. This interruption can cause the wave to enter a state of resonance, where it is unable to move and its amplitude grows dramatically. This resonance occurs for specific patterns, identified as wave numbers 6, 7, and 8. A wave number of 6, for instance, signifies 6 full ridge and trough cycles wrapping around the hemisphere. When the atmospheric conditions are just right for these particular wave numbers, the entire pattern can get stuck. Petukov's paper was a foundational step, and the field has advanced significantly since. From the perspective of current events, one of the most critical follow-up studies was a 2020 paper in Times Nature Climate Change Times by a team including Kai Kornhuber and Daniel Kumu, titled "Amplified Rossby Waves Enhance Risk of Concurrent Heat Waves in Major Breadbasket Regions." Their work examined the historical record for simultaneous heat extremes across the Northern Hemisphere. They focused on events where multiple major agricultural zones, separated by thousands of kilometers, suffered extreme heat at the same time. The study uncovered a shocking link. When the planetary wave pattern locked into a wave number of 5 or 7, the likelihood of these concurrent extremes rose by up to a factor of 20. The impacts on agriculture were also quantified, showing an average global reduction in major crop production of about 4%, with some regions facing losses as high as 11% during the most severe years. The physical process, described in the Kornhuber paper, is precisely what unfolds during these events. When a Rossby wave locks into a high-amplitude, low-speed state, the areas beneath its persistent ridges are subjected to continuous high pressure. This forces air to descend, which suppresses cloud formation, lowers humidity, and allows for intense, uninterrupted solar heating of the ground. After just a few days, the surface becomes hot. After a week, it can lead to record-shattering temperatures. This is a self-reinforcing pattern that does not easily dissipate. For the wave to break, it requires a significant disruption from an external source, such as a Madden-Julian oscillation from the tropics, a shift in the North Atlantic storm track, or a stratospheric sudden warming event that disturbs the polar vortex. This describes the ridge, but every wave has two sides. At the opposite end of the same stationary wave, the trough is also locked into place, anchored by the temperature difference between a cold air mass to its north and a warm one to its south. This trough becomes a focal point of instability. The energy gradient across it fuels persistent storm patterns, like those seen in the Central Plains. This mechanical coupling is the key to understanding the system's persistence. The ridge and the trough are two faces of a single, unified wave, and they are forced to endure together. To break the ridge, you must break the entire wave, which in turn releases the trough. They are fundamentally inseparable and must be disrupted as one. The current atmospheric setup appears to match the very wave number 5 to 7 signature that the Kornhuber paper highlighted as the highest risk pattern for simultaneous extremes. The wave is locked, its amplitude is high, and its phase speed is low. A trough is positioned over the Great Basin, while a ridge sits over the western Atlantic, with other corresponding features across the Pacific. This pattern of roughly 5 to 7 stationary highs and lows around the hemisphere is the classic signature of resonance. It is this single, overarching, resonant wave that can explain the simultaneity of seemingly unrelated weather events, such as a blizzard in Wyoming, occurring at the same time as a heat dome over New England. They are simply different expressions of the same planetary phenomenon. This body of research continues to expand, with scientists now examining other long-term impacts of these stalled atmospheric patterns. A 2021 study in Times Water Resources Research from a team that included Wan Han delves specifically into the question of persistence. The paper, titled On Low Phase Speed Rossby Wave Packets and Persistent Drought in the Western United States, explored the historical connection between these slow-moving wave packets and the location and duration of regional droughts. This work adds another crucial layer to our understanding, linking these atmospheric traffic jams not just to acute weather events, but to long-term climatic conditions like drought. The research uncovered a statistical association between low phase speed packets and persistent regional droughts. The underlying mechanism involves slow-moving high-pressure systems that can sit over the same areas for weeks on end, which in turn prevents precipitation systems from reaching them. This is the same dynamic we are watching unfold right now. The Bermuda High, which is currently anchoring the eastern ridge, is a classic low-phase speed feature. It is sitting stationary off the east coast, refusing to move, and in doing so, it is trapping warm continental tropical air over the land. This behavior perfectly matches what the Han paper described, providing a stark, real-world example of the science in action. However, there is another part of the scientific literature that is more difficult to discuss, as it suggests that these destructive patterns are occurring more frequently than our climate models have predicted. This concern was detailed in a follow-up paper from Kornhuber and others, published in 2023 Inches, Times Nature Communications. The title itself is a warning. Risks of synchronized low yields are underestimated in climate and crop model projections. The paper's central argument is that the models we rely on to project our future climate, specifically the CMIP6 suite, which is the current generation of models used in IPCC assessments, fail to adequately reproduce the resonance behavior that leads to these concurrent extreme events. The reason for this discrepancy, the paper suggests, lies in structural biases within the models themselves, particularly in how they represent the upper-level jet stream. The models tend to depict the jet stream as slightly too zonal, meaning too consistently west to east, and they do not sufficiently amplify the atmospheric waves. But when you compare the model outputs to actual observations from recent decades, a different picture emerges. The observations show significantly more amplification and a greater frequency of synchronized extremes than the models had forecasted. This reveals a critical gap between our projections and the unfolding reality. The core implication of the 2023 Kornhuber paper is that we are likely underestimating both the future frequency and the intensity of days just like this one. While the models calculate that events like today's should happen with a certain predictable frequency, the observational record indicates they are happening more often. This means the climate of the next 20 years will probably contain more of these extreme configurations than our projections currently show. Whether that translates to 1 extra event per decade or 5 depends on the precise magnitude of the model bias and the specific climate scenario, neither of which is yet settled. But the direction of the error is clear. The models are underpredicting the risk. You can stack the body of scientific evidence right next to what is happening on the screen, and the pieces fit perfectly. The atmospheric wave is in the wave number range that Petukov's research said gets stuck. Its amplitude is in the range that Kornhuber identified as producing a 20-fold increase in concurrent extreme risk. Its phase speed is low, in precisely the way Hahn's work said produces persistent regional anomalies. The events on the surface, the blizzard, the heat dome, the tornado outbreak, and the fire weather are the very concurrent extremes that the literature predicted this configuration would generate. And according to the 2023 Kornhuber follow-up, the frequency of this entire configuration is probably underestimated in the models we use to project what the next 2 decades will look like. This is the crucial context people miss when they talk about a heat wave as a single, isolated anomaly. Today's event is not just a heat wave, it is a configuration. This configuration is producing the heat wave on one of its faces, while simultaneously producing a blizzard on the opposite face. It is generating a tornado outbreak on the trough's eastern flank and extreme fire weather from the descending dry air on the trough's backside over the southern Rockies. The configuration produces all 4 of these faces at the same time because they are all part of the same atmospheric wave. And this wave is in a state that climate science has been describing with increasing precision for the last 12 years. This state is not some random, unnamed phenomenon. It has a name, a distinct wave number signature, and a statistical fingerprint. It has been directly linked in peer-reviewed papers to devastating consequences like crop failures, widespread drought, and concurrent heat extremes. The pattern we are seeing did not emerge from nowhere. It is exactly what the scientific literature described. Yet, the wave did not amplify in a vacuum. It intensified into preconditions that had been building for months. This is the next part of our story, for if the amplification was the trigger, these preconditions are what loaded the gun. Part 5. How the drought loaded the heat dome. The first precondition is a subject we explored in our Calm Space feature from May 12th, the worst spring drought across the United States in the modern instrumental record. The National Centers for Environmental Information maintains a climate division dataset that goes all the way back to 1895, giving us 131 years of operational climate observation. Within that long history, the period from January through April 2026 was the second driest on record, surpassed only by the year 1910. The Palmer Drought Severity Index, or PDSI, for March 2026 was a staggering negative 7.85, followed by negative 7.56 inches April. To put those numbers in perspective, the only months in the entire 131-year record with lower PDSI values were July and August of 1934, at the very bottom of the Dust Bowl. By late April, 43.8% of the lower 48 states was in D2 or worse drought, the largest such footprint since August of 2012. By May 5th, 44% of the contiguous United States was rated D1 or worse. The drought in Florida was particularly severe, peaking at 99% state coverage in late April, with 78% in D3 and 22% in D4, the most intense drought footprint in Florida's 5-year monitoring history. This is the loaded gun. The parched land surface across more than half the country is the backdrop against which today's eastern ridge is building. The reason this dry backdrop matters so much for a heat dome is explained by a piece of physics that often gets a paragraph in atmospheric science textbooks, but rarely makes it into broadcast meteorology. The concept is called soil moisture-atmosphere coupling. The pathway was quantified in a 2019 paper in the Times Proceedings of the National Academy of Sciences, Times by a team that included Diego Morales at Ghent University. This research helps connect the dots between the ground beneath our feet and the air above our heads. The Morales paper found that under dry land surface conditions, the likelihood of extreme heat increased by about 30% when compared to wet land surface conditions. This effect was most pronounced during the transition seasons of spring and early summer, which is precisely the time frame of the current event. The physics behind this effect is remarkably straightforward once you see it. When the sun shines on the surface of the Earth, that incoming radiation has to go somewhere. Some of that energy is reflected back into space, a process governed by the surface albedo or its brightness. The rest of the energy is absorbed by the surface, which means it must eventually be released back into the atmosphere. There are two main pathways the surface uses to release this stored energy. One is called sensible heat, where the surface simply gets hot and warms the air directly through contact and conduction. The other pathway is known as latent heat. When water evaporates from a surface, it carries a tremendous amount of energy along with it. This occurs as the water changes from a liquid into a vapor, a transition that requires approximately 2.5 million joules of energy to convert just 1 kilogram of water. This energy is drawn directly from the surface and transferred into the atmosphere, not as heat you can feel in the air, but as latent heat stored within the water vapor. What this means is that the availability of surface water fundamentally dictates how incoming solar energy is distributed. It's a critical partition between sensible heat, which raises air temperatures, and latent heat, which does not. If a surface is wet, covered by damp soil, transpiring forests, lakes, or rivers, the majority of the sun's energy is channeled into this process of evaporation. The result is that the air remains cooler. During a heat wave, temperatures over a wet landscape are often several degrees cooler than they would be over a dry one, receiving the exact same amount of sunlight. But when the surface is parched and there is no water to evaporate, the equation changes entirely. All of that incoming solar energy must be released as sensible heat, causing the air to grow intensely hot and temperatures to spike. This very mechanism is why the Dust Bowl summers of 1934 and 1936 were so devastating. With no moisture to evaporate across the Great Plains, the sun's radiation went almost entirely into heating the air. The resulting combination of high pressure aloft, a dry surface below, and a persistent atmospheric ridge produced surface temperatures that shattered state records, many of which still stand today. A 2009 paper by Cook, Miller, and Sager quantified this effect, finding that the extreme heat of the Dust Bowl was substantially amplified by the arid land conditions. They calculated that land degradation and dust aerosols contributed an additional 1 to 1.5 degrees of warming, beyond what the large-scale weather pattern alone would have generated. It's a stark reminder of how the ground beneath our feet can intensify the sky above. The very same principle that amplified the Dust Bowl heat waves is now at play in the Eastern Heat Dome today. A prolonged drought over the last 6 months has left a continental-scale dry land surface stretching across the southwest, the southern plains, and the southeast. Across this vast region, soil moisture is in the bottom 10th percentile of historical values for this time of year. According to a 2019 study by Morales, the shift from a wet to a dry landscape under a heat dome of a given strength increases the likelihood of extreme heat by around 30%. This added probability helps explain why Boston, for example, is forecasting atmospheric anomalies 2 to 3 standard deviations above normal. While the high-pressure ridge would have formed regardless, it is the parched land beneath it that is driving surface temperatures to such dangerous heights. This stands as the first crucial precondition for the current event. The second precondition is a more recent development, an aerosol unmasking pulse that began in 2020. In January of that year, the International Maritime Organization enacted a new global sulfur cap for marine fuel. known as the IMO 2020 regulation. Before this regulation, ocean-going vessels ran on bunker fuel with a sulfur content of around 3.5%. After 2020, that limit was slashed to just 0.5%. This change caused a dramatic, overnight reduction in sulfate aerosol emissions over the world's oceans, with emissions dropping by roughly a third, particularly over the busy shipping lanes of the North Atlantic. When sulfate aerosols enter the atmosphere, they act as a faint reflective shield, scattering incoming solar radiation back into space. This has a cooling effect, reducing the amount of energy that reaches the planet's surface. Removing a significant portion of these aerosols, even just a third, diminishes that cooling effect. The atmosphere, it turns out, is highly sensitive to such changes in its chemistry. While the overall radiative forcing change was small in absolute terms, its impact was magnified by being concentrated over a specific region of the ocean. In 2023, a paper by James Hansen and a team of co-authors quantified this effect. They determined that the IMO 2020 regulation produced an effective radiative forcing increase that is contributing approximately 0.05 degrees Celsius of additional warming per decade. Their paper attributes the acceleration in global warming observed since 2023, what some scientists term the warming pulse, to a combination of this aerosol unmasking, the natural transition out of the 2020 to 2023 triple dip La Niña, and the steady background warming from ongoing greenhouse gas emissions. The Hansen paper sparked considerable debate upon its publication and has since been examined by other research groups, including a Cornell team in 2025 and a counter-analysis from Quaglia and Viziani in 2025. While the precise magnitude of the effect is still a subject of scientific discussion, the direction of the effect is not. For the weather patterns unfolding today, the North Atlantic is where this all comes together. The shipping corridors in this region saw the most concentrated removal of aerosols, and as a consequence, its sea surface temperatures have been running warmer than the modern baseline for nearly 3 years. This anomalously warm North Atlantic serves as the upstream condition for the Bermuda High. Warm sea surface temperature anomalies in the North Atlantic are known to favor a Bermuda High that is both stronger and extends farther to the west. When this high-pressure system pushes more westward than usual, it becomes much more effective at trapping warm air over the east coast for extended periods, blocking the advance of any incoming weather systems. This is precisely the dynamic that is occurring today. The third precondition is the ongoing ENSO transition, the Oceanic Niño Index, which is the key measure of the El Niño Southern Oscillation, stood at -0.55 during the last quarter of 2025. By the early months of 2026, it had risen to +0.11. Although the official state is neutral, the trend is clearly toward a warmer phase. In May, the NOAA Climate Prediction Center issued an El Niño watch, citing an 82% probability of its onset between May and July. The atmospheric component of ENSO, the part that directly influences mid-latitude weather, has not yet fully coupled with the ocean, but it is showing the first signs of doing so. Why does this matter for today's heat? Historically, these transitional states from La Niña to El Niño favor amplified ridging east of the Mississippi River. The mechanism is only partly understood, but it involves the redistribution of heat in the tropical Pacific, which in turn alters the position of the subtropical jet stream. This shift then influences storm tracks and determines where persistent high-pressure systems are most likely to anchor. Whatever the precise mechanics, the empirical record is clear. Similar transitions in the springs of 2014, 2015, and 2023 all featured amplified eastern ridging at some point during the transitional window. The Bermuda High is simply doing today what it tends to do during these periods of change. Finally, all of this is unfolding against a deeper background. the mega drought baseline that has been the focus of our calm space features from May 12th and the follow-up on May 16th. A 2022 study by Williams, Cook, and Smerdon, published in Times Nature Climate Change, used tree ring data reaching back to the year 800 to make a profound discovery. They determined that the period from 2000 to 2022 marked the most arid 2-2-year interval that southwestern North America has endured in at least 12,200 years. The research went further, attributing a significant 42% of this deficit in soil moisture directly to anthropogenic climate forcing. This so-called megadrought is more than a regional story. It has become the foundational state upon which today's weather patterns are constructed. The parched earth that now intensifies heat domes is a product of immediate weather conditions, seasonal dryness, and this 2-decade-long depletion of regional moisture. This sets a sobering stage, suggesting that the ground beneath our feet holds a deep memory of a climate in transition. To understand the severity of the current event, we must consider a confluence of stacked preconditions. Since 2020, a pulse of aerosol unmasking has altered the radiative balance over the North Atlantic, warming its sea surface temperatures. This, in turn, has reinforced and expanded the Bermuda high-pressure system westward. At the same time, a transition in the El Niño Southern Oscillation, or ENSO, has repositioned the jet stream and storm tracks in a way that favors atmospheric ridging in the east. Adding to this, a seasonal drought has left a vast expanse of dry land across the southern plains, the southwest, and parts of the southeast. Finally, the underlying megadrought has diminished the deep moisture reservoirs that would typically buffer short-term events like this one. It is a stark reminder that major weather events are rarely born from a single cause. While any one of these factors alone would be insufficient, their combination creates a uniquely volatile environment where a single trigger, an ejecting upper trough, can amplify a Rossby wave into the powerful configuration we now observe. What is perhaps most striking is that none of these contributing factors are a surprise. They are not unknown variables, nor have they been concealed by any agency or institution. On the contrary, each piece of this complex puzzle is openly documented in peer-reviewed scientific literature and tracked by operational monitoring systems. The drought status is available in the weekly USDM product, and the state of ENSO is detailed in the CPC's monthly bulletin. The influence of aerosol forcing is outlined in the seminal Hansen paper and its successors, while the megadrought baseline is described in the Williams paper. The very mechanism of Rossby wave amplification is explored in studies by Pico and Kornhuber. The data is public, the components are documented, and the science has been studied for years. This raises a crucial question. If the science is so clear, why do these events still feel so shocking when they arrive? The novel aspect, and the open question now facing the scientific community, is not about any single precondition, but about their combination. Scientists are grappling with whether the convergence of these factors is fundamentally altering the warm season climatology. Are the days when a wave amplifies into this dangerous configuration becoming more frequent? And are the climate models used to project the next 20 years underestimating how often this will happen? A 2023 paper in Times Nature Communications Times by Kornhuber suggests that they are. The next generation of climate models, the CMIP7 suite currently in development, will likely attempt to correct for this bias, though time will tell. For today, the relevant fact is that the preconditions behaved exactly as the literature predicted they would. The trigger arrived, the wave amplified, and we are now watching the result unfold. This means that today is not a single, isolated anomaly. Instead, it represents the moment that 4 distinct anomalies, which built separately over months and years, have converged. The seasonal drought, the warm Atlantic, the ENSO transition, and the megadrought baseline have all come together in one powerful Rossby wave amplification. Each of these elements has its own distinct character, and it is these individual faces that we will now explore. Part 6 of our story examines the plains outbreak, which is the trough's other face. The first manifestation of this system, visible on radar east of the Rockies this afternoon, is a tornado outbreak across the plains. At 12:46 Coordinated Universal Time today, the Storm Prediction Center in Norman, Oklahoma, issued a Day 1 convective outlook. This outlook included a moderate risk area, a significant alert covering portions of central and northeast Kansas, southeast Nebraska, and far northwest Missouri. To appreciate the gravity of this forecast, it is helpful to understand its context. A moderate risk is the fourth tier on the 5-level categorical risk system used by the SPC. It sits just one step below a high risk, a designation reserved for days like the 27th of April, 2011, when a truly historic and widespread severe weather event appears likely. Historically, a moderate risk is issued on only about 4 to 6% of all Day 1 outlooks. This is a useful number to keep in mind. On average, the moderate risk language is used on about 20 days each year, with most of these occurring during the primary severe weather season from late April through early June. Today is one of those days. The situation is made even more exceptional by the fact that on this same day, other agencies are issuing their own severe warnings. The SPC is also forecasting an extreme tier fire weather risk on the southern high plains, while the Weather Prediction Center has identified a moderate risk for flash flooding over central Missouri. This combined categorical stack of extreme hazards places the day in the top decile of multi-hazard events in the historical record for May. The narrative from the SPC is particularly telling, as it details the specific threats forecasters were anticipating. The bulletin warned that supercells, with the capacity to generate very large to giant hail, alongside multiple strong to intense tornadoes, were most probable in a corridor stretching from central Kansas and southeast Nebraska into Iowa and northwest Missouri. For meteorologists, these are not just words, but precise codes for potential devastation. The hail forecast was specific, indicating the potential for very large to potentially giant hail with diameters of 2 to 4+ inches. Hailstones larger than 2 inches in diameter, roughly the size of a hen's egg, are the threshold at which you begin to see roof damage on residential structures. When hailstones reach the 3-inch range, the size of a baseball, they can shatter car windshields and pockmark the siding on houses. At 4 inches, the size of a softball, hail can cause structural damage to vehicles and can be lethal to anyone caught outside without shelter. The language used for the tornado threat was equally specific. Strong to intense tornadoes is the operational vocabulary the SPC uses for tornadoes rated EF2 and higher on the enhanced Fujita scale. An EF2 tornado, with winds of 111 to 135 miles per hour, can cause significant structural damage, including the loss of roofs and exterior walls on well-built homes. An EF3, with winds of 136 to 165 miles per hour, is the point at which well-built houses can be leveled. An EF4, at 166 to 200 miles per hour, can sweep well-built houses clean from their foundations. While the SPC was not explicitly forecasting EF4 or EF5 language, the phrase multiple strong to intense tornadoes clearly communicated that the office expected more than one tornado of at least EF2 intensity across the outbreak area. A significant severe weather outbreak is taking shape across a specific corridor of the American heartland. The geography of concern encompasses central and northeast Kansas, stretches into southeast Nebraska, and covers northwest Missouri. Major cities lying in the path of these storms include Salina, Topeka, Manhattan, Lawrence, and the Kansas City metropolitan area. In Nebraska, the risk extends through the Lincoln and Omaha corridor, while in Missouri, it includes Street, Joseph, and the suburbs of Kansas City. This places a population of approximately 3 million people under a moderate risk for severe weather. For many, they reside in urban centers where emergency management and well-practiced warning systems are in place. Yet, the storm's path will also traverse smaller, rural communities, raising questions about vulnerability and preparedness in these more isolated areas. The timeline for this event is just as specific as its location. The Storm Prediction Center's narrative indicates that robust thunderstorms are expected to ignite between 18:00 and 22:00 Coordinated Universal Time. For residents on the ground, this translates to a window between 1:00 p.m. and 5:00 p.m. Central Daylight Time. The first cells are forecast to fire along a dry line in central Kansas around 1:00 p.m., beginning a steady march to the east-northeast at a speed of 30 to 40 miles per hour. By late afternoon, around 3:00 or 4:00 p.m., these storms will have reached northeast Kansas, where they are expected to consolidate into powerful supercells. As evening approaches, between 5:00 and 6:00 p.m., the system will move over southeast Nebraska and northwest Missouri, an area where the low-level wind shear is predicted to be at its strongest. This sets the stage for the most dangerous period, with the highest risk for significant tornadoes falling between 4:00 p.m. and 8:00 p.m. However, atmospheric science is rarely simple, and forecasters have identified a potential limiting factor that introduces an element of uncertainty. This wildcard is an outflow boundary left over from a cluster of thunderstorms that occurred earlier in the day near the Missouri-Illinois border. These boundaries, which are essentially the leading edges of cool air spreading out from decaying storms, can have a dual effect. They can act as a focal point for new storm development, even helping to break through atmospheric caps that would otherwise prevent storms from forming. Conversely, they can also disrupt the environment by spreading a layer of cooler, more stable air, which can suppress afternoon storm redevelopment. The final position of this boundary is being watched closely, as it will determine whether the forecast verifies as written, needs to be expanded, or ultimately underperforms. This brings us to a larger, more profound question. Why is this severe weather event unfolding today, and how does it connect to other extreme weather happening across the continent? The answer lies in a vast, continent-spanning atmospheric feature known as a Rossby wave. The same upper-level trough that is digging into the Great Basin and fueling a blizzard in Wyoming is also the engine, ejecting energy out of the Rockies and into the Central Plains. This trough represents the western half of the Rossby wave. Its eastern counterpart is a large ridge of high pressure situated over the western Atlantic. These two systems, the trough and the ridge, are mechanically coupled. They amplify each other and cannot exist in isolation. It is this intricate dance of atmospheric forces that sets the stage for such disparate yet connected weather events. The trigger for the storms in the Central Plains is a smaller disturbance, a short wave that is being ejected from the main trough. As this energy moves into the plains, it initiates a powerful atmospheric process. At low levels, it pulls warm, incredibly moist air northward from the Gulf of Mexico. Simultaneously, a strong southwesterly flow aloft brings in cold, dry air at the mid-levels of the atmosphere. This stark temperature contrast between the warm, moist layer below and the cold, dry layer above is what creates profound instability, a measure known as convective available potential energy, or CAPE. An atmospheric sounding taken this morning from Dodge City revealed extreme mid-level lapse rates of 9 degrees Celsius per kilometer. This is among the steepest lapse rates one can observe in the plains during a severe weather setup. providing the raw power needed for the forecast of very large to giant hail and the potential for strong, intense tornadoes. So, when the Storm Prediction Center issues a moderate risk for tornadoes in central Kansas, they are describing more than just a local weather event. They are, in fact, describing the eastern flank of the very same weather system that has a blizzard warning in effect over Interstate 80 inches Wyoming. The wave's western trough carves into the Great Basin, while the eastern edge of that trough flings energy into the plains. This energy collides with the warm, moist air drawn up from the Gulf, a flow driven by the same broad pressure gradient that is pushing southerly winds up the east coast toward Boston. That southerly flow on the east coast is what amplifies the Bermuda High, creating a heat dome. Over the plains, that same pattern of southerly flow provides the essential moisture supply for tornadoes. They are, in essence, two different outcomes of the same atmospheric current. The system's vast eastern footprint is clearly visible in Severe Thunderstorm Watch number 220. This watch, active until the early evening, covers a wide swath of the Midwest, including central and east-central Illinois, the northern Indiana corridor through Fort Wayne and South Bend, the Indianapolis metro area, parts of Michigan through Lansing, and a portion of Ohio. The list of affected areas reads like a tour of the region, from Chicago and Indianapolis to Champaign-Urbana, encompassing the entire I-65 corridor from Indianapolis north to Gary. It is a testament to the sheer scale of the atmospheric disturbance driving the day's weather. Bringing the focus back to the heart of the risk area, the local National Weather Service offices provided clear and direct warnings. The office in Topeka, Kansas, stated in its hazardous weather outlook that severe thunderstorms were expected after 3:00 p.m., potentially forming into a line as they move east. They highlighted the main hazards as very large hail, damaging wind gusts, and a few strong tornadoes. They also noted a concern for localized flooding in areas that had already received heavy rain. The language from the office in Wichita, Kansas, was even more explicit. Their outlook warned that scattered thunderstorms would redevelop and that some could quickly become severe, producing significant severe weather. The forecasters there warned that the stronger storms would be capable of producing damaging winds around 70 miles per hour, hail up to the size of baseballs, and, most ominously, a few strong tornadoes. Across the Central Plains, official discussions echo a consistent and severe forecast, detailing the potential for powerful thunderstorms, very large hail, destructive winds, and strong tornadoes, all accompanied by heavy rain. By evening, these storms are expected to consolidate into a line as an advancing cold front overtakes the region of warm, unstable air. This line of storms will then track eastward through the night and into Tuesday morning. As the week progresses, the primary threat is forecast to shift, moving south into Texas and the lower Mississippi Valley by Tuesday afternoon. By Wednesday, the entire weather pattern is projected to weaken as the atmospheric trough moves on. But the most immediate and dramatic consequence of this system is a tornado outbreak across the plains. This outbreak is just one manifestation of a single powerful weather wave, a wave that is simultaneously responsible for a blizzard in Wyoming and a building heat dome over New England. It is this same system that pulls moisture northward, feeding the storms. Yet, this wave has a fourth, more subtle face, one that becomes visible only when we turn our attention to the southern high plains, where a protracted drought has now collided with ferocious winds. To understand the danger here, we must look to the fire weather outlooks issued by the Storm Prediction Center, which uses a tiered system of risk. The first level is elevated, indicating that conditions are favorable for the spread of any fires that might start. The next tier is critical, which warns of rapid fire growth and conditions that would make containment difficult. The highest operational category is extreme. This designation is reserved for situations that support explosive fire growth, the potential for embers to be carried long distances, and fast-moving, wind-driven fires capable of overwhelming initial firefighting efforts. Beyond this, the SPC has no higher standard category for its daily outlooks, which speaks to the gravity of an extreme forecast. It represents the ceiling of predictable danger. On this day, the 18th of May, 2026, the fire weather outlook is exceptionally rare, with all three tiers, elevated, critical, and extreme, active at the same time. The footprint of the extreme risk area is cast over the southern high plains, a region encompassing the panhandles of Texas and Oklahoma, the eastern third of New Mexico, and the western edge of Kansas. This is the very same corridor that was under a critical risk just 2 days earlier, on May 16th, signaling a significant and rapid intensification of hazardous conditions. The situation has clearly escalated, raising the question of what specific factors are driving this dramatic increase in risk. The underlying mechanism is a direct consequence of the large-scale weather pattern. The same upper-level trough generating the blizzard and the tornado outbreak is also driving powerful westerly winds down the eastern slopes of the southern Rocky Mountains and out onto the high plains. As this air descends, it undergoes adiabatic compression, a process that causes it to warm and dry out substantially. For every kilometer of descent, the air temperature rises by approximately 10 degrees Celsius, while its relative humidity plummets. The result is a surge of exceptionally hot, dry air at the surface. Today, this will cause temperatures across the Texas Panhandle to soar into the upper 90s and even exceed 100 degrees Fahrenheit, with relative humidity dropping into the single digits. This morning's discussion from the Weather Prediction Center was unambiguous. Forecasters stated that strong westerly winds descending from the southern Rockies would encounter dry ground and extremely low humidity, creating extreme fire weather danger across the southern high plains. They noted that this threat would persist until a cold front arrives from the north on Tuesday, bringing much cooler air. The forecast also highlighted that temperatures would again surpass 100 degrees in the hottest locations of the Texas Panhandle before the cooler air mass moves in overnight. This creates a dramatic meteorological contrast, with a day of intense, dangerous heat giving way to a significant drop in temperature. To place this in context, a 100-degree day in the Texas Panhandle in May is not entirely without precedent, but it is far from normal. The average high temperature for Amarillo in May is in the mid-70s. Since record-keeping began in 1892, the hottest May temperature ever recorded there is 103 degrees. However, it is the convergence of multiple factors that makes today so perilous. The combination of 100-degree heat, wind gusts reaching 35 to 40 miles per hour, and relative humidity in the single digits places this event in the far tail of the climatological distribution for fire weather. It is this simultaneous alignment of heat, wind, and dryness at their most extreme values that justifies the extreme risk designation. The state of the landscape is the final element that makes this situation so dangerous. For the better part of the last 6 months, the southern high plains have been gripped by drought. The region's grasses and rangeland vegetation are either dormant or dying, their moisture content far below the thresholds that fire managers consider safe. As a point of comparison, field samples taken by CAL FIRE in early May showed that the moisture content of chaparral in California was in the high 70s to low 80s%, a level of dryness not typically seen there until mid to late June. This same dynamic is now at play across the southern high plains. The fuel has been cured by the drought, making it exceptionally receptive to ignition. When you combine this cured fuel with intense wind and exceedingly low humidity, The result is a day with a high probability of ignition and conditions that promote high-consequence fire spread. A key metric used in fire forecasting, the Energy Release Component, or ERC, quantifies this danger. This index, which has been a staple of fire weather prediction for 4 decades, integrates fuel moisture, temperature, humidity, and wind into a single number. Today, across the southern high plains, the ERC is projected to be at the 90th percentile of all historical values for this date. This is an operationally significant threshold, indicating that the fuel bed is as dry and volatile as it has been on the very worst fire weather days ever recorded for this time of year. The official response to these conditions is already underway. Earlier this morning, the National Weather Service office in Hanford, California, issued a red flag warning for the West Side Hills and the San Joaquin Valley. The warning's text is concise and direct, noting wind gusts of 35 miles per hour and humidity of 15% or less, lasting through Monday evening. It identifies the highest threat as fast-moving grass fires and states that any fires that develop will likely spread with great speed. The language is stark and operational, a clear signal of imminent danger that leaves no room for misinterpretation. This warning is not an isolated event. Across the country today, 15 separate red flag warnings are active, along with one no weather watch. The geography of these alerts traces a vast fire weather corridor, stretching across much of the American West. The warnings are issued by a network of National Weather Service offices, from Amarillo covering the Texas and Oklahoma panhandles, to El Paso for southern New Mexico, and Albuquerque for the state's central and eastern zones. The corridor continues westward, with the Flagstaff office covering Arizona's high country and the Las Vegas office responsible for southern Nevada and northwestern Arizona. Together, their alerts paint a picture of a continent-spanning region primed for fire. In California, a powerful and persistent wind corridor has been influencing conditions for the better part of 2 weeks. This corridor stretches from the state across the Four Corners region and into the southern high plains, reaching the Texas and Oklahoma panhandles. The NWS offices in Sacramento and Hanford, which monitor the Central Valley and its foothills, have been tracking this phenomenon. Today, the winds within this corridor are peaking, with gusts reaching the highest levels forecast all month, creating a situation of heightened alert. Separately, a distinct but equally concerning weather event is unfolding in Southern California, where the NWS Los Angeles Oxnard office issued an update about a late-season Santa Ana wind event taking shape across the San Gabriel Mountains. Gusts between 25 and 40 miles per hour are already being observed, with some hotspots recording speeds in excess of 50 miles per hour. These powerful Santa Ana winds are the Southern California equivalent of the Diablo winds known farther north. Both are types of downslope winds, characterized by their warmth and dryness. Their formation is a fascinating and potent meteorological process, initiated when a pressure gradient develops between a high-pressure system over the Great Basin and a lower-pressure system off the coast. This differential effectively pulls air from the interior, forcing it over the mountains. As the air descends through the canyons toward the coast, it accelerates, compresses, and warms, shedding its moisture. By the time this air mass reaches the metropolitan areas, its relative humidity can plummet to the teens or even lower, while temperatures climb several degrees higher than they would be otherwise. An occurrence of Santa Ana winds in May is quite rare, though not entirely unprecedented. The climatological season for these winds typically runs from October through April, making this a late-season event. On average, a May Santa Ana might happen only once every 3 to 5 years. Such an event requires a specific atmospheric setup. A deep upper-level trough must dig into the Great Basin, establishing the kind of strong inland high pressure that fuels the Santa Anas. The system observed this morning is precisely that kind of trough, creating the perfect albeit unusual, conditions for this phenomenon to materialize. This situation has prompted significant concern from the Los Angeles office regarding fire weather, particularly across the San Gabriel and Santa Susana mountains. The danger lies in the convergence of multiple factors. The strong offshore winds are blowing across a landscape that has endured a long stretch of warm, dry conditions. This has left the fuel bed, the vegetation that could potentially burn, exceptionally dry after 2 full weeks of drying out. It is this combination of wind, low humidity, and critically dry fuels that elevates the risk of a fast-moving and difficult-to-control wildfire. The gravity of this situation is underscored by the recent history of wind-driven fires in this corridor, as explored in a previous feature on Calm Space from May 16th. The historical fire reference class for these events is sobering. We are reminded of the Camp Fire on the 8th of November 2018, where Diablo winds fueled a blaze that claimed 85 lives in Paradise, California. The Tubbs Fire of the 8th of October 2017, driven by a similar Diablo pressure gradient, resulted in 22 fatalities in Sonoma County. More recently, the Marshall Fire of the 30th of December 2021 destroyed 1,084 homes in Boulder County, Colorado, amid gusts of 110 to 115 miles per hour and relative humidity of 20 to 25% conditions. So extreme, they forced the NWS Boulder office to re-evaluate its red flag warning thresholds. The Smokehouse Creek Fire on the 26th of February 2024 burned over 1 million acres in the Texas Panhandle, with 500,000 acres consumed in the first 12 hours under winds exceeding 60 miles per hour. And the Carr Fire of the 26th of July 2018 in Redding, California, generated a fire vortex with damage equivalent to an EF3 tornado in residential areas. What makes today's forecast so alarming is that the conditions in place across the southern high plains are, in some respects, more severe than those that preceded many of these historical catastrophes. The Camp Fire was driven by gusts in the high 50s to low 60s, while the Tubbs Fire saw similar wind speeds from its Diablo pressure gradient. The Marshall Fire was an outlier, with its extreme 110 to 115 miles per hour gusts. But the Smokehouse Creek event was fueled by winds over 60 miles per hour across a 150-mile corridor. Today, the Southern High Plains corridor is experiencing sustained winds of 35 miles per hour, with gusts reaching 45 to 50 miles per hour, single-digit relative humidities, and air temperatures around 100 degrees Fahrenheit. All of this is occurring over a fuel bed that has been in drought for 6 months, creating a truly hazardous combination. The structural conditions for a major fire are unquestionably present. Maintaining the position of careful restraint that we strive for on Calm Space, the most honest framing is that today represents a high probability day for ignition under conditions that would lead to high consequence spread. It is crucial to note that the threat lies in the conditions themselves. A fire has not yet started. However, should an ignition occur in this fuel bed this afternoon, the potential for a major event is incredibly high. The contingency, the great unknown, is whether an ignition source will appear, be it a lightning strike from a dry thunderstorm, a spark from agricultural equipment, an arc from a downed power line, or a carelessly discarded cigarette. Fire managers in the corridor are acutely aware of this threat, and Type 3 incident management teams in the rural Texas Panhandle and eastern New Mexico are prepositioned for just such a contingency. The common thread tying this all together is the underlying drought, the same parched land surface that is amplifying the eastern heat dome through the soil moisture atmosphere coupling pathway we covered previously, is the very same dry surface that has made the fuel bed so receptive to ignition today. The 2019 finding by Morales, which identified a 30% greater likelihood of extreme heat over dry land, represents one face of what drought can do. The other face is visible today in the energy release component, a measure of fire potential, which is running at the 90th percentile over the southern high plains. It is the same drought, producing two distinct but equally dangerous consequences within a single weather wave. So, three faces of this immense weather wave are visible today: a blizzard in Wyoming, a tornado outbreak across the central plains, and extreme fire weather in the southern high plains. But there is a fourth face, one held in the soaked river basins of Missouri. The Weather Prediction Center has placed a moderate risk for flash flooding on the map for central Missouri this afternoon, revealing another dimension of this system's power. There are, of course, other stories unfolding today. A geomagnetic storm watch is in effect. An asteroid is projected to pass closer than the Moon tonight, and there are volcano updates from the Pacific. While some viewers may be tempted to fold these events into the same narrative, they are not part of this weather wave. Some are real, significant events, but none are physically connected to what is happening across the continent today. This distinction is critical, as it separates a story with a discernible physical mechanism from a pattern created by selective attention. The fourth face of the wave is the one we turn to now. This fourth face manifests as the moderate risk of flash flooding issued by the Weather Prediction Center for central Missouri. The mechanism behind this threat is straightforward. Repeated rounds of training thunderstorms are expected to pass over the same corridor. Each storm will drop a significant amount of rain, and because the ground is already saturated from previous rainfall, the water will have nowhere to go but into rivers and streams, leading to rapid rises in water levels. The cumulative effect of these storms is what creates the high risk of flash flooding. The same atmospheric river of moisture that is fueling the severe thunderstorms and tornadoes to the west is being funneled into this region, where it will be wrung out repeatedly. This highlights the interconnectedness of the weather phenomena within this single massive system. The same wave that brings fire risk to the plains and blizzards to the mountains also brings the threat of devastating floods to the river valleys. It is a stark reminder of the multifaceted and powerful nature of large-scale weather patterns. A corridor of significant flood risk stretches across a large portion of the lower Midwest, beginning in eastern Kansas and extending through Missouri, southern Illinois, and into western Kentucky. The scale of this atmospheric event becomes clear when we look at the waterways. As of this morning, 21 separate flood warnings are active on rivers throughout the lower Midwest and along the Gulf Coast. In Louisiana, for instance, both the Vermilion River at Lafayette and the Calcasia River near White Oak Park are experiencing minor flooding. The powerful Missouri River is in flood at multiple locations, including Napoleon, Waverly, Glasgow, and Miami, impacting a vast number of counties from Jackson and Ray all the way through to Washington and Franklin. Further minor flooding is reported on the Blackwater River and the Crooked River, with 10 flood watches running in parallel, a testament to the widespread saturation. The engine driving this threat of flash flooding is a familiar one, fueled by the same atmospheric dynamics creating the tornado outbreak on the Central Plains and supporting the heat dome in the east. A southerly low-level jet is diligently pulling moisture from the Gulf of Mexico northward into Kansas and Nebraska. As this system moves, some of that moisture is deposited as heavy rainfall along its eastern flank. Here, the moisture is forced upward over a warm front boundary situated across central Missouri, triggering intense precipitation. This process is amplified by a training mechanism, where storms repeatedly form and move over the same area, leading to the dangerous flash flood scenarios we are witnessing. It is a complex dance of atmospheric forces. The trough provides the lift, the Bermuda High supplies the moisture, and all of it unfolds as part of the same large-scale wave pattern. However, Not all stories unfolding in our skies today are part of this specific atmospheric wave. It is crucial to distinguish between events that are physically connected and those that simply occur at the same time, a distinction that requires careful attention to the underlying mechanisms. The first of these parallel, or off-wave, stories is a geomagnetic storm watch issued by the Space Weather Prediction Center. This G1, or minor, geomagnetic storm watch is in effect for May 18th and 19th, following an announcement made on May 17th at 16:12 Coordinated Universal Time. The source of this alert is a coronal mass ejection that departed the Sun on May 16th. According to the modeling, this CME is expected to deliver only a glancing blow to Earth. The bulk of the ejected plasma is projected to pass just north of our planet, with the peripheral interaction likely to produce only minor geomagnetic activity. The forecast anticipates a peak KP index of 5.33 during the 03:00 to 06:00 UTC window on May 19th, a value that just crosses the threshold into the G1 storm category. This raises the question, what does this actually mean for us on the ground? The potential impacts are minimal, limited to weak power grid fluctuations at high latitudes and a chance for aurora to be visible across the northern tier of the United States. In essence, this is a low-end space weather event real, but not a driver of the terrestrial weather patterns. In a related but separate development, active region 4436 produced a notable C9-7 solar flare on May 17th at 20:53 UTC. This event was accompanied by a significant radio burst, but critically, no Earth-directed coronal mass ejection was observed. This is the very same active region that generated the M5-7 flare we explored on Calm Space back on May 10th. Now, 10 days later, the region has rotated to the Sun's western limb, past its Earth-facing position, and is producing less powerful flares. Simultaneously, the flux of high-energy electrons has been elevated since May 16th, peaking at 6,120 particle flux units. This is well above the 1,000 unit alert threshold, a level that certainly commands the attention of satellite operators due to the risk of internal charging on spacecraft in geostationary orbit. While all of these solar and geomagnetic events are genuinely occurring, none of them are responsible for the Rossby wave shaping our weather. Geomagnetic storms primarily couple with the magnetosphere and the ionosphere, far above the troposphere, where weather happens. The energetic particle fluxes we're seeing, while a known hazard to satellite electronics, have no well-established, immediate effects on surface weather. The scientific literature exploring connections between the Sun and the troposphere is limited and tends to focus on long-term trends related to the one-year solar cycle, not on individual flares or CMEs. The current geomagnetic conditions are an interesting parallel phenomenon, but they are not the cause of the events unfolding on the atmospheric wave today. The second off-wave story involves the close approach of asteroid 2026 JH2. Tonight, on May 18th, at approximately 22:00 Coordinated Universal Time, the asteroid will pass about 91,300 kilometers from Earth. To put that in perspective, this is merely 0.24 lunar distances, well inside the Moon's orbit, though safely outside the ring of geostationary satellites. The object, estimated to be between 15 and 35 meters in diameter, is traveling at 9.14 kilometers per second relative to our planet. It was only discovered 8 days ago by the Mount Lemmon survey in Arizona, a reminder of the ongoing challenges in planetary defense that we have previously examined on Calm Space. Crucially, there is absolutely no risk of an impact with Earth tonight. The asteroid's trajectory is in no way connected to the atmospheric patterns dominating our weather. Its path was determined years, if not centuries, go by its own orbital elements, governed by the unyielding laws of gravitational mechanics. These cosmic mechanics operate on scales of time and energy that are completely independent of the weather systems on our planet. The fact that the asteroid's flyby coincides with this particular day of severe weather is just that, a coincidence, and nothing more. This brings us to a narrative that has been gaining traction on social media, one that seeks to connect these disparate events. This framework, sometimes called a convergence of energies or a great alignment, suggests that the simultaneous tornado outbreak, geomagnetic storm, asteroid approach, and heat dome are all evidence of a single, coordinated process. The idea of cosmic scale patterns or planetary harmonics has resonated with enough people that it warrants a direct and honest address. The simple truth, grounded in physics, is that there is no known physical mechanism that could possibly link these phenomena. The arithmetic of the energy budget makes this clear. The tidal force exerted on Earth's atmosphere by a perfectly aligned planet is approximately 1/10,000,000th of the force that Earth's own gravity exerts on the atmosphere every single moment. Even if we combine the cumulative tidal forces from all planetary alignments, the result is still thousands of times smaller than the tidal effect of our own moon, a force which is itself too weak to have any detectable influence on large-scale, synoptic weather patterns. Understanding these vast differences in scale is key to seeing the universe as it is, rather than as we might imagine it to be. When examining theories about widespread weather events, the numbers for the proposed cause and the observed effect must be in the same order of magnitude. A simple analysis of the energy budget helps to clarify the claims surrounding the High-Frequency Active Auroral Research Program, or HAARP. This facility transmits radio waves at a power of up to 3.6 megawatts. In stark contrast, the energy contained within a single Rossby wave, as it amplifies across the continental United States, is estimated to be on the order of 10 to the 25th joules. The transmitter is therefore incapable of injecting sufficient energy into the troposphere to influence or lock in a feature of this scale. Beyond the energy mismatch, the geometry is also incorrect. HAARP directs its transmissions upward into the ionosphere, not laterally into the lower atmosphere where weather phenomena occur. A 2024 paper from the United Nations, published in Atmospheric Chemistry and Physics, serves as a canonical reference for this energy budget, concluding that no plausible transmitter could generate the large-scale atmospheric circulation being observed. The concept of cloud seeding falls into a similar category of misapplied scale. While cloud seeding is a genuine technology, its effects are well documented and limited. Under specific conditions, particularly the presence of supercooled liquid water in clouds already poised to precipitate, it can enhance rainfall by a modest 5 to 15%. However, this technology cannot conjure a continental Rossby wave from scratch, nor can it trap a vast system like the Bermuda High in place. It cannot, for instance, generate a blizzard warning over a wide region that wasn't already subject to the necessary synoptic conditions for snow. The underlying mechanism, which involves augmenting the rate of ice nucleation in existing cloud water, is fundamentally local and stochastic in nature. It is a tool for influencing weather on a local scale, not for engineering the climate of a continent. Similarly, the chemtrails narrative fails when scrutinized against the aerosol mass budget. Even with the most generous interpretations, the total mass of aerosols emitted by commercial aviation is several orders of magnitude smaller than what would be necessary to affect a circulation feature spanning an entire continent. The natural aerosol burden, which includes wind-lofting dust during dry periods, biomass smoke, and sulfates, is vastly larger over the continental United States than any contribution from aviation. A second critical flaw in this framing is the geographic mismatch. Commercial aviation traffic is concentrated along specific corridors, and these routes show no correlation with the locations of events like a blizzard in Wyoming. Here again, the numbers tell a story that diverges sharply from the narrative of a hidden program. Another proposed explanation, which connects current geomagnetic conditions to extreme weather, also fails on the grounds of the energy budget. For decades, scientists have studied the electrical processes that couple geomagnetic storms to the magnetosphere and the ionosphere. Yet, the subsequent coupling of that energy down into the troposphere, where our weather happens, is weak at best. A 2020 paper by Marchitelli in Scientific Reports did establish a statistical correlation between solar activity and seismic events, but it could not be used to predict individual earthquakes. Furthermore, follow-up research in 2026 by Mizuno, Kao, and Umio in Kyoto confirmed that this effect is small and limited to seismic activity, not synoptic-scale meteorology. While the current geomagnetic conditions do constitute a real space weather event, they are not the driver of the atmospheric wave pattern causing this weather. Where skepticism is warranted, and what gives these alternative explanations such power, is the very real and unusual simultaneity of the events themselves. The narrative circulating on social media that something unprecedented is happening is, in a sense, partially correct. The specific combination of operational extremes we are witnessing is indeed rare. The error in this framing, however, lies in attributing this rarity to clandestine human actions or vast cosmic forces. The actual cause is well understood within the scientific community and requires no such extraordinary explanations. It is the result of a Rossby wave amplification occurring during a transitioning El Niño southern oscillation, compounded by anomalous soil moisture, elevated background temperatures, and aerosol levels. The answer, it seems, is not hidden in conspiracy, but is written in the language of atmospheric science. In fact, the science itself is entirely open. The foundational papers by Kornhuber, Williams, and Hansen are publicly available, as are the raw data feeds from the National Weather Service. Nothing is concealed. The conspiracy framings attempt to explain a phenomenon that already has a robust scientific explanation. And within that scientific explanation lies a genuinely open question, which is where our focus should be. A 2023 follow-up paper by Kornhuber in Nature Communications presented an argument that has not yet been fully absorbed by the operational forecasting community. The paper argued that the climate models used to project weather for the next 20 years are systematically underestimating the frequency and intensity of resonant Rossby wave configurations like the one driving today's events. The reason for this underestimation, the paper suggests, is that the models possess structural biases in how they represent the upper-level jet stream. They tend to simulate a jet stream that is slightly too zonal, flowing too directly from west to east, and as a result, they do not amplify the atmospheric waves enough when model outputs from recent decades are compared to direct observations. The observations consistently show more wave amplification and more synchronized extremes than the models had predicted. This raises a critical question about our future. If the Kornhuber 2023 argument is correct, and the empirical evidence gathered so far supports it, then days like today are occurring more often than our climate projections anticipated. This discrepancy between models and observations is what makes this an active, vital area of research, not a settled matter. The pattern of 5 simultaneous operational extremes, driven by a single wave on one calendar day in May, is not a once-in-a-decade event in this emerging climatology. The models might suggest a frequency of once every 10 to 15 years, but observations from the last decade point to something closer to once every 3 to 5 years. This disagreement highlights how much more we need to learn. For the forecasts leading into June, July, and August of this year, this implies that the atmospheric configurations producing concurrent extremes, the simultaneous heat domes, droughts, fire weather, and severe storm days that were historically rare, are very likely to repeat. Looking ahead, the Climate Prediction Center's outlook for June through August 2026 continues to favor above normal temperatures across most of the country. An El Niño watch is in effect, with an 82% probability of onset by July. This transitional state is one of the historical conditions known to favor amplified atmospheric ridging. Once the El Niño signal fully couples with the atmosphere, the wave configuration we are witnessing today may shift from being a transient mid-May event to a recurring feature of the summer. This leads to a final, sobering realization. Our warning systems were not designed for what may come next. The National Weather Service is built around individual hazard categories: severe weather watches, fire weather outlooks, heat advisories, and flood warnings. Each category has its own distinct product, a structure that may be ill-equipped to handle the interconnected, widespread, and simultaneous hazards of our new climate reality. Every piece of weather information is designed for a particular audience, flowing out to distinct sectors of our society. These include broadcast meteorology, emergency management, transportation, agriculture, and even healthcare. Yet, when 5 different categorical extremes manifest on a single day, the very structure of this communication system is strained. The audience receiving a heat advisory in Boston is entirely different from the one under a blizzard warning in Wyoming. Likewise, those under a tornado watch in Indiana are not the same group seeing a red flag warning in the Texas Panhandle. Each local office speaks to its own region, but this leaves a critical void. No single voice is discussing the vast atmospheric wave that connects and drives all of these events. This reveals a structural problem, where the atmosphere is behaving as one cohesive system, but our warning framework communicates it as 5 separate stories. The public hears 5 different narratives from 5 different agencies, and the crucial links between them may never be made clear. Fortunately, those dots can be connected. The physical connection even has a name, documented within peer-reviewed scientific literature: a quasi-resonant amplification, wave number 5 to 7 Rossby resonance, a low phase speed wave packet, or a mechanically coupled trough configuration. This is not some hidden secret. The mechanism is well understood. The issue is that this understanding is not yet integrated into the communication architecture of the National Weather Service. If days like today, marked by such widespread extremes, are indeed occurring more frequently than climate models had projected, then our methods of communication must evolve to keep pace. A fundamental shift in public awareness will be required. To truly grasp our changing weather, the public will need to understand what a Rossby wave is. There will need to be a broader recognition that a single atmospheric wave can simultaneously produce a stifling heat dome on one side of the continent and a heavy blizzard on the other, all on the same calendar day. People will need to see that the intense heat beneath an eastern ridge and the deep snow within a western trough are not separate phenomena, but 2 faces of the very same atmospheric configuration. This requires a new way of thinking, one that perceives the atmosphere as an interconnected system rather than a series of isolated local stories. This is precisely the kind of systemic understanding we have been cultivating here on Calm Space over the last few months. It is the reason our explorations of the drought on May 12th and the multi-hazard storm setup on May 13th resonated with our viewers. It is also why we consistently return to the same body of research studies from Williams, Cook, and Smerdon in 2022, Hansen in 2023, Hahn in 2021, and Kornhuber in 2020 and 2023, along with Morales in 2019. These papers provide the scientific architecture that explains what is happening when the atmosphere behaves as it did this morning. The audience that gathers here does not need to be told that a heat wave is hot. What this audience seeks is a deeper understanding of what is driving that heat wave, why it is occurring on the same wave as a blizzard, and what this configuration implies for the remainder of the warm season. It is a search for context, not just information. For now, this specific pattern is beginning to break down. A cold front is set to arrive on Wednesday afternoon, causing the eastern ridge to weaken and allowing the entire wave to finally progress eastward. The Bermuda High will retreat offshore, and by Thursday, the wave's amplitude is expected to fall back into a normal range. Consequently, high temperatures in the northeast are forecast to be 15 to 20 degrees cooler than Tuesday's peak. The forecast for Friday through the Memorial Day weekend points toward cool, near-seasonable temperatures, signaling the end of this particular event. But this is just one pattern. The literature suggests that the underlying configuration that produced today's events is becoming more common. The next time this type of wave amplifies, it will be on a different date, with a different set of specific conditions. The eastern ridge might establish itself over the southeast instead of the northeast. The western trough could dig into the northern Rockies. The simultaneous extremes might manifest as a combination of tornadoes, heat, drought, and flooding, perhaps without the snow component or with it. If the timing falls within a transitional month, the specific combinations will vary, but the mechanism will be the same. If you have been following our work on calm space for the last 6 months, you have already witnessed this mechanism produce concurrent extremes on several occasions. The bi-coastal heat dome from May 8th was an early version of today's configuration, showing a coast-to-coast signature. The inland migration on May 9th was that same wave shifting its anomaly westward and into the high plains. Our multi-day pattern analysis from May 13th explicitly identified today as the verification for the eastern rebuild. The fire weather corridor on May 16th was the southern flank of the same trough affecting the southern high plains. And the Everglades fires, around May 11th, were a different wave, but one performing a similar trick over Florida. Today's event is simply the most visible instance of the mechanism because its spatial signature includes a blizzard warning that is impossible to ignore alongside an East Coast heat dome that everyone can feel. So, what can be done with this knowledge? What is the takeaway from understanding that the atmosphere is doing something the models did not fully anticipate, on a date that historically has not produced such a combination of simultaneous extremes? The most honest answer is to watch. Pay attention to the pattern when it forms. You can learn to recognize the signature of an amplified Rossby wave on a 500 millibar chart. It is something any weather enthusiast can do with just 20 minutes of focused attention on a single map. You can learn to ask, when the local forecast calls for unusual heat or snow, what the synoptic pattern is doing on a larger scale. Through this process, you learn that May heat on the East Coast is not separate from May snow in Wyoming when they happen on the same day. You learn to think of the country as a connected weather system, not as 50 separate states. And with this understanding, you can begin to plan for the recurrence of this configuration. This is not because every day will be like today, but because the days that are like today are becoming more common, and the next one may arrive with a different combination of extremes on a different date. Looking ahead, the Climate Prediction Center's summer outlook continues to favor above normal temperatures for most of the country. An El Niño watch remains in effect through the summer, though the atmospheric ENSO signal has not yet fully coupled. The wave configuration we see today is one of the patterns known to produce the kinds of concurrent extremes that we have been observing more often than models had led us to expect. The next pattern is already on the horizon. It might be a week away, or it might be a month away, but it will not be much longer than that. For now, the cold front arrives Wednesday afternoon. The heat dome retreats Wednesday night, and in Wyoming, the snow tapers off this evening, bringing a temporary calm. The tornado outbreak across the plains is forecasted to intensify between 4:00 p.m. and 8:00 p.m. Central Daylight Time this afternoon. In a separate extreme, a corridor of dangerous fire weather will persist until a cold front arrives on Tuesday, with conditions finally moderating by Tuesday night. This specific pattern is expected to conclude by Friday, allowing seasonable weather to return for the holiday weekend. And yet, what we are witnessing is something profoundly new. The atmosphere has orchestrated an event today with a combination of intensities that no one alive has ever seen before. 5 simultaneous categorical extremes, all stemming from a single wave on one calendar day in May. The common thread is a Rossby resonance, a vast atmospheric wave running from the Pacific Northwest to the Western Atlantic. The patterns that generate such events are not only real, but they are appearing more often and arriving earlier in the year than scientific models had anticipated. The literature describing these mechanisms is public and well established. The only true unknown is how many more days like today this year holds, and with what amplified intensity they will arrive. The wave responsible for this remarkable alignment is projected to break apart by Wednesday night, but a new wave is already visible in the data, waiting to assemble. By next weekend, we will have a clearer picture of whether this powerful pattern intends to lock back into place. The first indications will come from the position of the Bermuda High and the depth of any new trough forming over the Great Basin. If these two features converge again, the pattern is effectively reloaded. If they do not, the continent may experience a few weeks of calmer, more seasonal weather before the atmosphere makes its next attempt. In either scenario, what we are observing is not a singular, isolated event. It is a glimpse into what our atmosphere is becoming. Days like today, with their simultaneous extremes and record-breaking potential, are not the last of their kind. Instead, they represent the early instances of a new and more volatile normal. To grasp the full weight of this phenomenon, we must look beyond the immediate meteorology. A 2020 paper by Kornhuber and his colleagues examined the crop losses associated with resonant events involving wave number 5 and wave number 7. Their findings were stark. The most severe configurations led to regional agricultural losses on the order of 11%. While a figure like 11% may seem modest on paper, its meaning transforms when considered in the context of global food security. The world's major breadbasket regions, including the United States Midwest, the European Wheat Belt, the Black Sea Grain Corridor, the Chinese North Plain, and the Indian Indo-Gangetic Plain, collectively produce over half of the planet's caloric supply from staple grains. An 11% reduction occurring simultaneously in just 2 or 3 of these regions within the same year would represent a food supply shock that the international grain trade was never designed to absorb. The 2020 paper explicitly identified this vulnerability as its most policy-relevant finding, a conclusion that was reinforced by a follow-up study in 2023. These studies tightened the case, showing that climate models were failing to capture the full risk of concurrent extremes. Observational data revealed that synchronized crop failures were happening more often than the models had projected. This moves the conversation from the abstract to the immediate. The implications for global food security are not a distant, theoretical concern. They are an operational challenge that is unfolding right now. What we are witnessing this morning in the United States is the effect of one wave number on a single continent. But the very same kind of pattern can trigger simultaneous extremes across multiple continents when the resonance is broader, a fact clearly documented in the scientific literature. Indeed, history provides clear examples of this global reach. The summer of 2010 saw a devastating Russian heat dome occur concurrently with catastrophic monsoon flooding in Pakistan, both driven by a single wave number 7 configuration. The summer of 2018 brought another wave number 7 event, which unleashed simultaneous extremes across Europe, North America, and East Asia. The summer of 2022 saw a similar pattern repeat. These are not random occurrences. They are recurring, well-documented phenomena confirming that the underlying atmospheric patterns are both real and repeating. This raises a critical question for the scientific community. The question of whether our predictive tools are keeping pace with reality is one the modeling community is actively wrestling with. Researchers are now developing the CMIP 7th generation of climate models for the next IPCC assessment, hoping they will more accurately reproduce this resonance behavior. Early indications suggest the new models are an improvement over the previous generation, but they are not yet perfect. The gap between what is modeled and what is observed is narrowing, but it has not been closed. This tells us that there is a longer story arc at play here, and that arc is not yet finished. Today's pattern is just one instance in a longer sequence that will continue to unfold, continue to be documented in peer-reviewed literature, and continue to produce the kinds of operational anomalies we have been watching this month. The drought, the heat domes, the complex multi-hazard storms, the corridors of fire weather, and the simultaneous coast-to-coast extremes all share a common driver. That driver has a name, and that name is appearing with increasing frequency in both operational forecasts and research papers. The mechanism is no longer hidden in obscure academic journals. The names are public, the literature is open, and the forecasts are improving. Even as long-term projections still lag behind the observable reality. Tomorrow, as the records fall and broadcast meteorologists report on the story of the heat, you will understand something deeper. You will know that the heat is merely one face of the same wave that delivered a blizzard warning to Wyoming this morning. You will know this wave is in a configuration that the climate science community has been describing for the past decade. You will also know that this configuration is happening more frequently than the models predicted it would. And perhaps most importantly, you will know that the question of what comes next after this particular wave breaks on Wednesday night is the question to which nobody yet has an answer. A cold front will arrive, the pattern will reset, and the atmosphere will return to a state of apparent quiet. Then, sometime later this summer, the wave will amplify again. The next time, it may not look anything like today. The only thing it is guaranteed to share is the underlying mechanism. A mechanism we are going to be seeing much more of. This is the open loop in the system. This is what is far from over. The wave that created today's extremes is not the last of its kind. The configuration we are watching is an early version of what the atmosphere is now capable of doing in the middle of May. And so, the most honest framing is the one we must leave you with. The science is open, the mechanism is known, the pattern is happening. The truly urgent question is not what the atmosphere did today. The question is how many more days like today the rest of this year is going to contain. When the answer arrives, it will likely emerge not as a sudden discovery, but as a quiet signal within a forecast model, appearing 5 days in advance. This information will be handled with the same deliberate caution officials in Boston recently demonstrated. A particular phrase may become more common in these vital discussions. Close to the maximum relative to climatology. It is a term to listen for,